On the morning of April 3, 1945, at precisely 0820 hours, Lieutenant Colonel Thomas Bradford stood on the flight line at Fliegerhorst Biblis Airfield near Mannheim, Germany, examining what would become the most heavily armed twin-engine fighter aircraft to fly combat missions in World War II. Before him sat Lockheed P-38L Lightning, serial number 4425474, and positioned on wooden cradles beside the aircraft were two complete M3 75mm tank guns salvaged from destroyed M4 Sherman tanks. The tanks had been knocked out during the Rhine crossing operations, but their main armaments remained intact and functional. The P-38L Lightning represented the most advanced variant of Lockheed's distinctive twin-boom fighter design. Powered by two Allison V1710-111/113 engines, producing 1,600 horsepower each with war emergency power, the aircraft could reach speeds of 414 miles per hour at 25,000 feet. The central nacelle, positioned between the twin booms, housed the cockpit and all armament, one 20mm Hispano AN M2 cannon, and four Browning M2 50-caliber machine guns, all mounted in the nose. This concentrated firepower could be devastating against air and ground targets. By April 1945, American tactical air forces in Europe faced a persistent and frustrating problem. German armored forces were deploying their heaviest tanks in desperate defensive operations. Panther tanks with 80mm frontal armor, Tiger II tanks with 150mm frontal armor, and Tiger tank destroyers with 250mm frontal armor were appearing in increasing numbers. These vehicles were essentially immune to aerial attack by conventional fighter armament. The P-38's standard armament of one 20mm cannon and four 50-caliber machine guns was effective against most ground targets, but inadequate against German heavy armor. The 20mm rounds could penetrate approximately 25 millimeters of armor at close range, sufficient against half-tracks and light armored vehicles, but ineffective against tank armor. Even the top armor of Panther and Tiger tanks, the thinnest and most vulnerable area, was typically 40 to 50 millimeters thick. Fighter bombers carried bombs and rockets for anti-armor missions. The P-38 could carry two 1,000-pound bombs or 10 5-inch high-velocity aircraft rockets, HVAR. These weapons could destroy any tank with direct hits. However, accuracy was extremely poor. Bombs required precise release timing and perfect dive angles. Fighter pilots needed a weapon that combined the accuracy of guns with destructive power exceeding bombs. The M3 75mm tank gun represented the standard armament on early production M4 Sherman tanks. The weapon fired a 14.6-pound armor-piercing projectile at a muzzle velocity of 2,030 feet per second. At 500 yards range, the M3 could penetrate 68 millimeters of armor plate at 30-degree obliquity. This penetration capability was sufficient to defeat the side and rear armor of Panther tanks, the side armor of Tiger tanks, and potentially the rear armor of even the heaviest German vehicles. More significantly, the M3 fired a 75mm high-explosive shell that weighed 14.7 pounds and contained 1.47 pounds of explosive filler. This round, designed for engaging soft targets and fortifications, created massive blast and fragmentation effects. Against unarmored or lightly armored targets, trucks, half-tracks, buildings, bunkers, the 75mm high-explosive round was devastatingly effective. Two M4 Sherman tanks had been destroyed during fighting near Mannheim on March 28, 1945. One tank struck a mine that destroyed the running gear but left the turret intact. The second tank was knocked out by a German 88mm anti-tank gun that penetrated the side armor. Both vehicles were recovered by maintenance units. The hulls were damaged beyond economical repair, but the turrets and 75mm guns were salvageable. Colonel Bradford, commanding officer of the 474th Fighter Group, examined the salvaged M3 guns on April 2nd. Each complete gun assembly weighed approximately 1,140 pounds, including the breech mechanism, barrel, recoil system, and mount. The guns were 115 inches long from breech to muzzle. Bradford recognized immediately that these weapons, if mounted on aircraft, could provide anti-armor capability that no existing fighter possessed. The concept was audacious and technically unprecedented. No twin-engine fighter in American service mounted weapons approaching the size and power of a 75mm tank gun. The largest weapon commonly mounted on American fighters was the 37mm cannon on the P-39 Airacobra, and that weapon fired projectiles 1/5 the weight of 75mm rounds. The M3 gun was designed for installation in armored fighting vehicles with massive structural strength and weight, not in aircraft optimized for lightweight and aerodynamic efficiency. However, the P-38's unique design offered specific advantages for mounting large weapons. The twin-boom configuration created a wide stance that could potentially accommodate outboard weapon mounts. Each boom contained an engine, providing structural strength and the potential for mounting heavy equipment. The aircraft's total empty weight of 12,800 pounds and maximum takeoff weight of 21,600 pounds suggested it might be able to carry substantial additional armament. The tactical potential was extraordinary. A P-38 mounting two 75mm tank guns could engage any German armored vehicle with weapons that guaranteed penetration of vulnerable areas. The accuracy of fixed forward-firing guns, combined with the destructive power of 75mm ammunition, would make the modified P-38 the most effective anti-armor aircraft in any air force. The psychological impact on German tank crews, knowing that aircraft could destroy their vehicles with direct cannon fire, would be substantial. Bradford examined the M3 guns throughout the afternoon of April 2nd. The weapons were in excellent condition, despite the tank destructions. The barrels showed minimal wear. The breech mechanisms functioned properly. The recoil systems were intact. The guns required only minor cleaning and inspection before being serviceable. The question was whether they could be mounted on an aircraft and whether the aircraft could survive the recoil forces. At 1600 hours, Bradford convened a meeting with Major Robert Chen, the group's senior engineering officer, Captain William Morrison, the armament officer, and two Lockheed Field Service representatives stationed at Biblis to provide technical support for P-38 operations. The proposal was straightforward but unprecedented. Install both M3 75mm guns on a single P-38L, one gun mounted beneath each engine boom. The engineering challenges were extraordinary and multifaceted. The M3 gun weighed 1,140 pounds, more than twice the weight of all the P-38's standard armament combined. Mounting two guns would add 2,280 pounds to the aircraft's empty weight, plus the weight of ammunition and mounting structures. The total additional weight would exceed 2,500 pounds, nearly 20% of the aircraft's empty weight. The recoil forces were even more concerning. The M3 gun generated approximately 28,000 pounds of recoil force when fired. In a tank, this force was absorbed by a 30-ton armored vehicle sitting on the ground with tracks dug into soil. In an aircraft, the same force would be applied to an airframe weighing less than 13,000 pounds empty, traveling through air at hundreds of miles per hour. The structural and aerodynamic effects were difficult to predict. Major Chen began structural analysis immediately. The P-38's engine booms were constructed with heavy-duty aluminum alloy frames and stressed skin. Each boom was designed to support an engine weighing approximately 1,400 pounds, plus associated systems, propeller, and turbocharger. The booms were the strongest structural elements of the aircraft aside from the main wing spar. Chen calculated that the 75mm gun could be mounted beneath the engine boom using a cradle assembly that would transfer loads to the boom's main structural frames. The gun would be positioned with the barrel extending forward beyond the propeller arc and the breech positioned beneath the engine. The mounting structure would need to distribute the gun's weight and recoil forces across multiple frame stations to avoid overloading any single structural point. The installation position would place the guns approximately 12 feet outboard from the aircraft's centerline on each side. This wide spacing created concerns about the effects of asymmetric firing. If only one gun fired, the recoil would create a powerful yawing moment trying to rotate the aircraft about its vertical axis. The pilot would need to apply rudder force to counteract this yaw. If the yaw was too powerful, it could cause loss of control. Ammunition storage presented severe limitations. The M3 gun used ammunition that was substantially larger and heavier than any rounds carried by aircraft. A single 75mm armor-piercing round with cartridge case weighed approximately 20 pounds. A high-explosive round weighed approximately 18 pounds. Standard tank ammunition storage consisted of 90 rounds for the 75mm gun, but this was completely impractical for aircraft installation. Captain Morrison proposed limiting ammunition to 10 rounds per gun, 20 rounds total. This minimal capacity would provide enough ammunition for realistic combat trials while minimizing weight. The ammunition would be stored in a magazine positioned directly behind the gun, with manual loading required after each shot. The manual loading would be performed by the pilot using a lever mechanism accessible from the cockpit. The weight analysis was concerning but potentially acceptable. Each M3 gun weighed 1,140 pounds. Each mounting cradle would weigh approximately 180 pounds. Each 10-round ammunition magazine would weigh approximately 200 pounds loaded. The total weight per gun installation would be approximately 1,520 pounds. Installing 2 guns would add approximately 3,040 pounds to the aircraft's empty weight. This additional weight would increase the aircraft's empty weight from 12,800 pounds to approximately 15,840 pounds. The gross weight would increase from a typical 17,500 pounds to approximately 20,540 pounds. This was within the aircraft's maximum takeoff weight of 21,600 pounds, but it left minimal margin for fuel, providing only approximately 1,000 pounds of fuel capacity, enough for perhaps 45 minutes of flight time. The performance penalties would be severe. The additional weight and drag would reduce maximum speed by an estimated 40 to 50 miles per hour. Rate of climb would decrease by approximately 30%. Range would be cut to less than 1/3 of normal. The aircraft would be slower, less maneuverable, and limited to short-range missions. These penalties were substantial but potentially acceptable if the combat effectiveness justified them. Lieutenant Colonel Bradford faced a critical command decision. The modification would require removing P-38L serial number 4425474 from combat operations for at least 3 weeks. The aircraft would undergo structural modifications that could potentially weaken the airframe if not executed properly. If the recoil forces exceeded structural limits, the aircraft could suffer catastrophic failure during firing tests. However, if the modification succeeded, it could provide a revolutionary capability against German armor. On April 3rd at 10 o'clock hours, Bradford authorized the modification. By 1300 hours, P-38L 4425474 was in the maintenance hangar with both engine booms prepared for modification. Major Chen and his 6 experienced aircraft mechanics began the installation work immediately. The Lockheed Field Service representatives provided structural analysis and technical guidance. The first step involved fabricating the gun mounting cradles. Chen designed a structure consisting of a steel framework that cradled the 75mm gun barrel and connected to reinforced attachment points on the engine boom structure. The cradle would mount at 4 locations on each boom: at the firewall frame, at the main wing spar attachment, at the mid-boom frame station, and at the aft boom frame station. The fabrication took 5 days of intensive metalwork. The cradle structure was built from steel tubing and steel plate with reinforcement gussets at stress points. The completed cradle for each gun weighed 180 pounds, heavier than Chen's initial estimate, but necessary for structural integrity. The cradles were designed to transfer both the static weight of the gun and the dynamic recoil forces to the engine boom structure. Installation of the reinforcement structure within the engine booms began on April 8th. Access panels were removed from the boom undersides to expose the internal frame structure. Additional aluminum alloy stiffeners were riveted to existing frames at each mounting point. These stiffeners distributed loads across larger areas of the boom structure, reducing stress concentrations. The M3 guns required preparation for aircraft installation. The standard tank gun mount included a massive recoil mechanism and traversing mechanism that were unnecessary and too heavy for aircraft use. Morrison and his team removed these components, retaining only the barrel, breech, and a simplified recoil mechanism. The modified gun assembly weighed approximately 940 pounds, 200 pounds lighter than the complete tank gun. Installation of the first gun occurred on April 11th at 0900 hours. A mobile crane lifted the 940-pound gun assembly and positioned it in the mounting cradle beneath the right engine boom. Alignment was critical. The gun barrel needed to point straight forward along the aircraft's longitudinal axis, and the bore axis needed to be level when the aircraft was in level flight attitude. The alignment process required 8 hours of careful adjustment. Chen used surveying equipment to verify that the gun barrel was parallel to the aircraft's centerline and that the elevation angle was 0 when the aircraft sat on its landing gear. The gun was secured to the cradle using 16 high-strength bolts through reinforced mounting points. The second gun was installed on April 12th using the same procedure. Both guns were now mounted, extending approximately 6 feet forward from the engine boom centerline. The barrels protruded ahead of the propeller arcs by approximately 2 feet. The installation was symmetrical, with both guns at identical positions relative to their respective booms. The ammunition magazine construction proceeded simultaneously with gun installation. Morrison designed magazines that held 10 rounds in a vertical stack positioned directly behind the breech. The magazines were fabricated from steel plate and weighed 40 pounds empty. Each loaded magazine with 10 rounds weighed approximately 200 pounds. The loading mechanism was entirely manual. The pilot would operate a lever in the cockpit that would withdraw the breech block, allowing a round to drop from the magazine into the chamber. Closing the lever would close the breech and ready the gun for firing. This manual process would take approximately 15 seconds per round, extremely slow compared to automatic weapons, but acceptable for a weapon intended for precision shots against high-value targets. The firing mechanism required integration with the aircraft's electrical system. The M3 gun used an electric firing solenoid that required 24 volts. The P-38's electrical system operated at 24 volts, providing direct compatibility. Morrison installed separate firing buttons on the control yoke, one button for the right gun, one button for the left gun, allowing the pilot to fire guns individually or together. The gun sight required no modification. The P-38L was equipped with a K-14 gyroscopic gun sight capable of computing lead angles for aerial gunnery. The sight could be calibrated for different weapons by adjusting range and ballistic settings. Chen calculated the ballistic trajectory for 75mm rounds and prepared calibration cards for the pilot. Ground testing began on April 14th. The aircraft was towed to a remote area of the airfield and secured with heavy chains to prevent movement. The guns were loaded with dummy rounds, inert projectiles with the correct weight but no propellant. The loading mechanism was tested through multiple loading cycles to verify reliable operation. Live firing tests were scheduled for April 16th at a designated weapons range 15 miles from Biblis. The aircraft was towed to the range rather than flown. Ground testing of the recoil forces was essential before attempting flight tests. Major Chen personally supervised the test setup. The aircraft was positioned facing a heavily reinforced test barrier at 200 yards range. Heavy steel cables were attached to the landing gear and anchored to concrete blocks buried in the ground. Additional cables were attached to the tail to prevent rearward movement. The entire aircraft was restrained to withstand thousands of pounds of force. Lieutenant Robert Hayes, the group's senior test pilot with over 500 combat hours in P-38s, was selected to conduct the firing test. Hayes started both engines and completed pre-firing checks. He loaded the right gun manually using the cockpit lever. The mechanism worked smoothly. He armed the firing circuit and prepared to fire. At 10:15 hours, Hayes depressed the right gun firing button. The result was immediate, violent, and alarming. The 75mm gun fired with a massive crack substantially louder than any weapon normally fired from aircraft. The entire aircraft lurched backward against the restraining cables despite both engines running at high power and the brakes locked. The right wing dipped noticeably from the recoil force. The steel cables groaned under the strain. The recoil forces exceeded even the most pessimistic predictions. The gun had generated 28,000 pounds of rearward force in approximately 8 milliseconds, essentially an instantaneous impact. The airframe had absorbed this force without visible damage, but the dynamic effects were severe. The airframe had twisted noticeably, and several inspection panels had popped open from the structural flexing. Hayes waited 5 minutes for the aircraft to settle, then fired the left gun. The same massive report, the same violent lurch backward, the left wing dipping this time. More inspection panels popped open. The landing gear struts compressed and rebounded violently. The aircraft's structure was being stressed in ways never anticipated by the designers. Post-firing inspection revealed serious concerns. Several rivets in the engine boom structure showed signs of shear deformation. The boom skin had buckled slightly near the gun mount locations. The wing attach fittings showed stress marks. The airframe had not failed catastrophically, but it had been stressed beyond normal limits. Multiple areas required repair or reinforcement. Major Chen spent 2 days analyzing the structural damage and planning modifications. The fundamental problem was that the recoil forces, while manageable in terms of total magnitude, were applied too suddenly for the airframe to absorb smoothly. The shock loading created stress concentrations that caused localized damage. Chen proposed a solution: install hydraulic recoil buffers between the gun cradles and the boom structure. These buffers would absorb the initial recoil impulse over a longer time period, perhaps 50 milliseconds instead of 8 milliseconds, reducing the peak forces applied to the airframe. The buffers would function similarly to the recoil mechanisms in the original tank installation, but would be lighter and more compact.